be taking a claim and you're going to have to determine from a particular situation what we would call the null hypothesis versus what would be the alternative hypothesis. Usually the null hypothesis is what we would consider, we call it the status quo, or it's business as usual, or it's not interesting. It's usually what I call the boring case. The null hypothesis is usually what's already happening. And the alternative hypothesis is when you're a researcher, you're trying to see if something different or unusual is happening. And so I have an example with another handout that we'll go through that involves Panera, and I can kind of talk through those things. Jen like legit made a handout, like made this handout, like not just like took it from other people, but like made an example. And the reason I did is because my boyfriend really likes the charged lemonades at Panera. They have an insane amount of caffeine in them. So much so that they've been in the news because people have died. Or at least the claim has been that they've died because of so much caffeine being in these charged lemonades. So like one Panera charged lemonade, if you get a 30-ounce one, is supposed to have 390 milligrams of caffeine in it. A single soda has about 34 milligrams of caffeine. So 390 is a lot of milligrams of caffeine. A lot of coffees have like 60 something. The really powerful coffees will have like 100 something. 390 milligrams of caffeine is a lot of caffeine to be in a lemonade. So in this particular scenario, Panera has advertised that a 30-ounce charged lemonade contains 300 milligrams of caffeine. This is true. I didn't make this up. I went to their webpage. This is what they said it has. And then I heard in the last week that they've discontinued this lemonade because seriously, they keep getting in trouble for this lemonade. So they're going to like pull it off the shelves. It's not completely gone in all the Paneras yet, but it's going away because their claim is that it contains 300 milligrams of caffeine. You work at the county health department and you've been asked to test this claim to see if it's accurate. So this could actually happen if there are lawsuits about your product. The county health department could come in and go, well, we better test this lemonade and see how much caffeine is actually in there. Yeah, that's right there. Your investigation finds that a random sample of 36 of these 30-ounce charged lemonades had a mean caffeine content of 406 milligrams with a standard deviation of 54 milligrams. Okay, so Panera says there's 390 milligrams on average in these charged lemonades. You take a sample of 36 of them, and your average is 406 milligrams. So we're wondering, is Panera lying? Is there more caffeine in this? I mean, 390 is already a lot, but is there actually more caffeine in there? Should we be concerned that there's even more than they're claiming? At a 5% significance level. So when we say significance level, that's the same thing as saying an alpha level. We could also say a 95% confidence level. So when we say a 5% significance level or alpha 0.05, that's very similar to your confidence intervals that you've been making where we say 95% confidence intervals. So that can be a little confusing because you're like, why are we doing the opposite number? It's just the way that we tend to talk about these things. Significance level versus your confidence interval, we talk about them as like inverses of each other. So at this 5% significance level, do you have enough evidence to reject Panera's claim? And that's another way of saying, do we have enough evidence to say Panera is lying? There's more caffeine in there than they're saying there is. So when you guys are doing hypothesis testing, what's usually happening is there's this claim or there's this business as usual. And then you as a researcher are looking at a sample that you've taken, because obviously you're not going to go test every single Panera lemonade that ever gets served, but you might take 36 of them and then test it and then go, do I have enough evidence to suggest that there's actually more caffeine in these drinks, or maybe there's less caffeine in these drinks, or do we find out that what we call the null hypothesis is the truth and that there really is just 390 milligrams of caffeine in these drinks? So the null hypothesis is what we consider business as usual. It's boring. So what would be boring as researchers is if we go in and we study 36 of these samples and we find out that there's 390 milligrams of caffeine in them. And we're like, yeah, that's what they said. Boring. Alternative hypothesis is interesting. So we want to know, do we get to reject the null hypothesis, or do we have evidence to suggest that maybe an alternative hypothesis is correct? Okay. There's different ways to write a null hypothesis versus alternative hypothesis scenario. Usually what you guys are going to be doing when we're talking about a null hypothesis is you're going to set up a situation with an equal sign. And so when we're talking about this particular situation and it says state the null and the alternative hypothesis, the way that we talk about a null hypothesis is we say H not is that little zero down there. The word not, N-A-U-G-H-T, is the word that I'm saying. It's not N-O-T, it means zero. H not means H sub zero. Okay. H not, when I go to write the null hypothesis, I'm going to say that that would be that the mean, which would be our population mean, the mu, is equal to, and normally, like if we're writing the general formula, you'd write mu naught, but in this particular case, what we're going to write down is what our business as usual claim is. We're going to write 390. So my null hypothesis is that we have 390 milligrams of caffeine in these drinks because that's what Panera says it is. That would be the boring scenario that Panera is telling us the truth. Okay. Now, the alternative hypothesis, there's different ways I could write an alternative hypothesis here. Here's the most common one. Okay, so my null hypothesis is that the mean amount of caffeine is 390 milligrams. My alternative hypothesis is that it's not 390 milligrams. When I say it's not, I mean it could be less than 390 milligrams, or it could be more than 390 milligrams. So this is what we call the two-tail hypothesis test, because I'm not telling you that it's higher or lower. I'm saying it's not that, so it could be higher or it could be lower. There's two different ways this could go. But you could also have a one-tail hypothesis test where you would say that your alternative is that the mean is actually greater than 390 milligrams, right? And so in that case, I could be saying, Panera is lying, there's more caffeine in there. Or I could also write another one-tail hypothesis test. Maybe I really like caffeine in my drink and I'm like, Panera is lying, there's less than 390 milligrams in there and I want all 390 of my milligrams. These are other ways that we could write our alternative hypothesis, but the most standard one that we see is that we just choose, we don't go one direction or another, we just say it's not 390. And then we look at what pops out to kind of help us tell, well, was it higher, was it lower? This is called the two-tail test, and it's the most common one. But it is possible for us to do a one-tail test, okay? I'm going to do a two-tail test today. Now, I have some other stuff up here that you can refer back to later if you're like, what the? Alpha equals 0.05. That's the probability of making something called a type 1 error. And a type 1 error is a situation where you mistakenly reject the null hypothesis when you shouldn't, when the null hypothesis is actually true. If we choose an alpha of 0.10, that's allowing for a 10% chance of making a type 1 error. So 5% chance would be if we have an alpha of 0.05. So this is a 5% chance of a type 1 error? If I change the alpha level, then I'm changing how much of a chance that I'm allowing for us to make a type 1 error. There's another kind of error called a type 2 error. And with a type 2 error, it's actually exactly the opposite. And so I wrote on your formula sheet that I gave you, I have a way to kind of help you remember the difference between these, because these get really kind of confusing and people are like, oh, I don't remember which one's a type 1 and type 2. So here's what I put down here for you. It might be helpful. A type 1 error is falsely thinking the hypothesis is true. I only use the word false in that one time. That's a type 1 error. A type 2 error is falsely thinking the hypothesis is false. So I said false twice. I put false here and false here. If there's 2 falses in your statement, then that's a type 2 error. So falsely thinking your hypothesis is true, that's a type 1 error. Falsely thinking your hypothesis is false, that's a type 2 error. Might be helpful, might not, but I thought I would say it anyway. Okay. So we'll go back to our scenario here. I'm trying to figure out, is Panera lying to us? So we need to calculate the appropriate test statistic. The appropriate test statistic, I believe at this point in time, matters which class you are in. So my Whitener people, she very specifically has said, if you did not get the population standard deviation, we're going to have to go with the t-test. So because all I did was I took a sample and I got 406 milligrams of caffeine, and my sample had a standard deviation of 54 milligrams. I don't know the population standard deviation. I know my sample standard deviation. So for Whitener's class, you got to do a t-test. If you're over in Lang's class, from your textbook at least, I don't know what he has told you, from your textbook at least, he's got the, if we are using a sample size that's big enough that we can go ahead and stick with our z-test, and the sample number that we use is 30. Since I'm collecting a sample of 36 charged lemonades, I can use a z for that. Now here's the good news. The actual calculation I'm about to do doesn't matter which test I'm doing. So this next step, you're going to do exactly the same thing regardless. You're just going to label it something different. So some of you will label it a Z and some of you will label it a T. But ultimately what you're going to do is take the 406 milligrams that I found from my sample, that's my X bar. I'm going to subtract my 390 milligrams, which is my null hypothesis amount. And we divide it by either our sample standard deviation or the population standard deviation if they gave it to us. They didn't give us the population one, they only gave us the sample one. So 54 goes in there. And then we divide it by the square root of our sample size. Now, my sample size is 36 for this one. For those of you who are going to be doing the t-test, in a moment, you're going to care about that 36 because that 36, you're going to subtract 1 from it to figure out your degrees of freedom. And that's going to be the thing that you use on your chart to go figure out your number. For my people who are doing the Z test, so my Lang people, you don't actually care about the 36. That part doesn't matter. So the 36 matters in terms of you getting to use the Z, but you don't have to use it on the table part. Now, this part of the calculation, again, still doesn't matter. 406 minus 390 is 16 over 54 divided by 6. So that's going to be 9. So calculation-wise, we got 16 divided by 9. $1.78 if I round it. For some of you, this is your Z alpha over 2. And for some of you, this is your T alpha over 2. So some of you are going to write Z alpha over 2 is equal to 1.78. And my whitener people, you're going to write T alpha over 2 is 1.78. Doesn't really matter yet, but it will matter in a second. Questions on what I've done so far? You doing okay? Yeah.
Sorry, I was just looking at the equation.
Yes.
And for like the bottom part, the test statistic.
Yes.
There's like a part where you can add. When does that really get implemented?
There's a part where you can add. Yes. So that's when you have two different populations. So we're on the one population. When we have two different populations, then we'll be on that other page. Yeah. I'm starting basic. I promise we will get harder. Okay. So now, what I want to do next is I want to find the critical value for my test statistic that determines whether or not I'm going to reject the null hypothesis or not. Okay. So I'm going to start by looking at this in terms of just a normal standard, like when I draw you the curve. So we're using alpha is equal to 0.05. And that means that when I draw you the little distribution thing, this is a two-tailed test. So this 0.05 needs to get cut in half, which is 0.025. So alpha over 2 means that I'm looking over at this little part of the tail. That percentage number there is 0.025. And then I'm looking over at this tail over here, and that's the other 2.5%. What that is, though, is that you're taking the 95% because this is when we talk about an alpha of 0.05, that's a 95% confidence interval, like when we were talking about for our last class, where we were talking about making our range between what's our lowest value to what's our highest value. We are going up to 95%. So if we're starting at 2.5% and I add 95 to that, that's 97.5. So this is at 0.975 right there. Okay, so let me grab the color. Okay. So over in this tail or in this tail are the two regions where I would be saying, hey, I have scores that are unusual enough that I would reject my null hypothesis. This range between here and here, this is all where I would keep my null hypothesis. So if I actually am below 2.5% of the data or I'm above 97.5% of the data, I'm going to say, oh, those are the unusual regions. Those are called my rejection regions. So this is a rejection region. And this is also a rejection region. Yes.
Sorry, how'd you find the 0.975 again? Sorry.
So when we're talking about a critical value of 0.05, then I want you to be thinking that we're talking about 0.95 being the region that is where your null hypothesis is gonna land. So when it's a critical value of 0.05, that's 5%. 95% of it is not going to be in the rejection region. So because this is a two-tailed test, what I'm doing is I'm taking that 5% and we're cutting it in half. So it becomes 2.5% or 0.025 when we turn it back into a decimal. So if I want this 2.5% here, that's actually easy because we're on this side of the graph. And so I just go ahead and put the 0.025 here. But over here, if I want to know what number starts my 2.5% on this side, you can either take 100% and subtract 0.025 and that'll give you the 0.975, or if you know that this is 95%, then you'll take the 95% and add it to that number and that'll give you that number. So two ways you can think about it. Either 1 minus 2.5% will give you that number there, or take the 2.5%, add the 95%, and that'll give you that number right there. So that we get our two rejection regions. All right. That's the like craziest part. Okay. Now that we know that, there's critical values depending on if I'm talking about a Z or I'm talking about a T. We're all used to the Z table like a bunch. So I'm going to write Z critical here. And for my Z critical, you guys have already done this with me. When we talk about a 95% confidence interval, which matches up with my 0.05 when we're talking about the same, like what was the word that I wanted now? Not confidence level. What was it confidence level? Now I'm getting my words all messed up. Significance level. That was the word I wanted. 5% significance level corresponds to your 95% confidence interval in terms of the Z thing that we cared about. What was the Z when we wanted a 95% confidence level? Do you remember? It was 1.96 when it was the 95%. 1.96 is our critical value when it's a Z. Now, if you didn't know that and you were like in the middle of a test and freaking out, but you have your Z table, you can find that information. I have the Whitener version, not the Lang version. I like this one better. If I'm looking for the 0.975, then we're in the middle of the table here and we're looking for 0.975. 0.975 is right here, and that corresponds to 1.96. I'm not down far enough for you to see that 6 part. 1.96 is where the 0.975 lands. So I gave you those numbers, but it came from the table. I didn't like invent it. It came from the table. That's if you're using Z. So my Lang people, if it's a 95% confidence interval or it's a 5% significance level, which means they gave you an alpha of 0.05. We're talking about a two-tailed test here, and so you want 1.96 to be your critical value. My T people, I'm going to write T critical. Here's where your degrees of freedom matter. Okay. Degrees of freedom is always going to be whatever the sample size is minus 1. So we had a sample size of 36. If I subtract 1 from it, we have degrees of freedom equal to 35 this time. Okay. All right, it's a different table. This table along the top, I'm looking for that 0.975 just like I was for the Z, but they actually like have it written on the top of the table for the T table. Woohoo. The other thing you're looking for is the degrees of freedom. So we said 35 degrees of freedom is along this side. It's underneath the V column here. So I need to go to the third column and down to 35, which is here. So 1, 2, 3. This is my critical number for T, 2.03. 2.03. Okay. Notice that these two numbers are not that different from each other, and that's why sometimes instructors don't make you switch over to the T at this point, because they're like, that number is not that different from that number. It's not going to change your final value all that much. In the actual world of statistics, we never use Z. Ever. It's always T. In the actual world of statistics. So I understand why a lot of the instructors switch over to this. Also, in the actual world of statistics, you will never use a table. You'll be using R or some other programming thing, and you'll type in the thing and it will spit out the number for you. You won't be hunting for it. So when people are like, well, how do I, and I'm like, the problem is in the real world, you would never do it this way, but this is how we do it in the class. Yes.
I think for a Z critical, we use like 95%, but then for T critical, we use 97.
You didn't actually, because remember, when I did my Z critical, we were talking about this distribution, and we said that 0.25 was there and 0.975 was here to get the 95% being in the middle of that. And so I looked for 0.975 on my Z. Here was my Z one. I flipped back here and I went to 0.975 right here. And that was the 1.96. So for both of them, I used 0.975 for both of them. It is the 95% confidence interval. When you're doing the 95% confidence interval, we put 2.5% in this tail and 2.5% in this tail. And so you say 1 minus the 2.5% to tell you where does that confidence interval end. And that's going to be at your 0.975. This is the confusing part. It's weird.
Okay.
Yes.
Just out of curiosity, when you're doing like the table, how come like they told you to do like n-1 for like degrees of freedom?
That is an amazing question to which my actual answer will be very unsatisfying. Degrees of freedom is supposed to be talking about like it changes how much error and things that we're willing to consider. In terms of how your brain is going to remember it, your answer is going to be, we do this because in the real world, this ends up being closer to the correct answer. Truly, up until the 1970s, they didn't do this. They used to just use this one because see, these numbers are pretty close. They're not that far off. These are both around 2, right? They're not that far off from each other. But they found that in actual practice, they got answers that were closer to the correct answer if they subtracted 1 from whatever the n was. So like literally, it's an unsatisfying answer. Why do we subtract 1? Because our answer ends up being a little bit better. But I'm about to show you again in this particular test, it actually doesn't matter. So this is why in a lot of cases, your instructors will still stick with the Z. Last year, the instructor stuck with the Z when as long as the N was bigger than 30, we didn't worry about T. This is the first year we've had to worry about T for things that were in that range, like 30 or bigger. We don't usually do this, but in the real world, you actually always use T. So it seems reasonable to me that they might want to switch over to the thing you're doing in the real world anyway. All right, here's the thing. I just moved away our test statistic, but we came up with 1.78 was our test statistic. Here's what we do now. The critical number is the thing that is dictating where your rejection region is. Okay, 1.96 when we're talking about Z. Do you remember how we have a Z that's positive over here and we have exactly the same number, but it's negative over here? So if this one's 1.96, then this one's negative 1.96. So in terms of our 1.78, we're over on the positive rejection side, not the negative rejection side, because it's a positive number. Is that okay? So I'm not looking over at this tail. I'm looking at this tail over here. Is that okay? So here's what you're considering. 1.78, I'm going to draw another little distribution. Let's say 1.78 is right about here. If we're talking about the Z critical value, for our rejection region that was over here, we said that the Z critical value was 1.96. So that's the start of our rejection region. If the number that we got for our test statistic is in the rejection region, then we get to reject the null hypothesis. So that means that it would have to be beyond 1.96 because 1.96 starts right here. But our number's over here. So we're not in the rejection region for my Z people. My Z people, we fail to reject the null hypothesis. So for Z people, since 1.78 is not past our Z critical of 1.96, we fail to reject. And you can write out the words null hypothesis, or you get to be lazy and put H naught right there, because that means the null hypothesis. So people like to use the symbol because it means way less writing. You fail to reject. H naught means I fail to reject the null hypothesis. Okay. That was the Z. I'm going to draw you another one. My T critical was 2.03, and that's what started my rejection region for my T distribution. But our number was 1.78. And so if the number was 2.03 or bigger, it would be in the rejection region, but our number is not over in the rejection region. And so also for the T, even though the numbers are different, I still failed to reject the null hypothesis. So it actually didn't matter whose class we were in. We still failed to reject the null hypothesis regardless. So I'm going to write for the T people, since 1.78 is not past our T critical of 2.03, we fail to reject the null hypothesis. What does that mean in terms of my Panera situation? Fail to reject the null hypothesis means I don't get to say there's enough evidence that Panera is lying. So even though those numbers look different, 406 milligrams versus 390 milligrams for the average, what that means is that it's actually not a big enough difference for us to say that if I tested enough of them, that it would still be about 390. I just tested 36 of them. I have a weird sample of 36 of them, but if I kept sampling, I'd probably still end up around 390, probably. Fail to reject the null hypothesis doesn't mean that the null hypothesis is true, but it means that I'm 95% sure that I made the right choice. That's what the 5% significance level is there. I'm 5% not sure that I made the right choice, but I'm 95% sure I probably made the right choice. So it's a pretty good guess. Okay. So some things matter a lot as to whether or not we're going to end up getting to reject or not for our null hypothesis. I'm saying let's consider exactly the same scenario over again. I'm not changing anything except that I'm going to test 49 lemonades instead of 36 lemonades. I'm going to do everything else exactly the same. And so I promise we don't have to do most of the calculations again. The only calculation I need to do again is find the Z or the T score. It ended up being the same calculation, but I take the 406, subtract the 390. We're still dividing by the standard deviation of our sample, which was 54. But this time, I'm taking the square root of 49 instead of 36 because our sample size is a bit bigger. And this is going to give me my new either Z or T, depending on which class we're in. The calculation is going to be the same though, so that part doesn't matter. So 16 on top divided by 54/7 gives me 2.07. Okay, so for some of you, this is your Z alpha over 2. You got 2.07. And for my whitener people, you got your T alpha over 2 is 2.07. But here's the deal. Nothing else about this problem is getting changed. So we're still using the same significance level of 0.05. So the graphs that I drew still apply in this case. This is the number now that we're using to compare. So if you're my Z people, my Z critical was 1.96. And so if we're beyond 1.96, we're actually in the rejection region. 2.07 is in that region now. 1.78 wasn't. It wasn't big enough. But because 1.96 is the number we're trying to beat, we beat it. So this one, we are going to reject the null hypothesis. Woo! So now I can say Panera's lying. I had to test some more. When I tested 36, I didn't have enough evidence. When I tested 49, I now have enough evidence to say they're lying. Probably. You can't guarantee it, but you can say you're pretty sure. If I do for T, that means I'm down on this one and our critical was 2.03. But 2.07 is past 2.03 as well. So for both of them, I ended up rejecting the null hypothesis this time. So I failed to reject for both of them the first time. Now I get to reject. So for both of them, so reject the null hypothesis. There is enough evidence at alpha equal to the 0.05 significance level to suggest the mean caffeine level is not equal to 390 milligrams. Because remember, my alternative hypothesis was that it's not equal to 390 milligrams. So when I'm rejecting the null hypothesis, there is enough evidence to suggest that it's actually not 390 milligrams. They might be lying. So I said, one of the things that's super important is our sample size. If we have a bigger sample size, we get a different result sometimes. So when we had a sample size of 36, I couldn't reject. When I had a sample size that was just a little bit bigger at 49, now I could reject the null hypothesis. That's one thing that can change it. Another thing that can change it is if I change the alpha, my significance level. So this time I only want an alpha of 0.10 instead of 0.05. So this is now a 90% confidence interval instead of the 95% confidence interval. They're not exactly the same thing, but they're kind of similar in how we think about it. So this means that when we go to draw our picture, in each tail of my rejection region, I now have 5% in my rejection region instead of having only 2.5% in my rejection region. So in this case, right here, I have 0.05 over in this tail. 5% is in this tail for my rejection region. And I need 5% in this tail. If I need 5%, 100% minus 5% is 95%. So right here is going to be 0.95. So that's instead of 0.975 this time, we only have to go to 0.95. And these are my rejection regions. So that means that my T critical and my V critical values are different this time. Let's do the Z critical first, because this one you might know because it was one of the 3 numbers that I gave you. If we're talking about 0.10 for the alpha, that's the same thing as me talking about the 90% confidence interval. Do you remember what that Z score was? 1.64, yeah, or 1.65. It's actually 1.645, so somewhere in there, but 1.65 is totally fine for what we're doing. 2 decimal places is cool. The critical. T critical, I actually have to go back to the table. And this time, I don't want the column with 0.975. I want the column with 0.95 because that also matches up with that number right there, 0.95. So I'm still going to go down to 35, but I want the second number instead of the third number. So now I have 1.69 is my T critical. So we went to degrees of freedom was 35 because I'm going back to our original scenario where we had 36 that we were sampling. And then I only want to go out to 0.95 this time. 1.69 is my number. Okay. So remember, we're talking about our original situation. Our original situation, remember the value that we got was 1.78. 1.78 is out beyond both of those numbers. And so again, just by changing the confidence level, now I am going to reject the null hypothesis for both of them. So I changed this problem 2 different ways. The first time I changed the problem by changing our sample size. The second time I left the sample size still at 36, but I changed our alpha level. And by making those changes, that was enough for both of them to now reject the null hypothesis, because I just need these numbers. Those are the numbers that are the critical numbers. If this number is bigger than those numbers, then you're in the rejection region. So because 1.78 is bigger than 1.69, or because 1.78 is bigger than 1.65, depending on whose class you're in, we reject. Okay. I know this stuff's a little weird the first few times you do it. So I would recommend kind of like, if you have a few minutes this weekend, to kind of go back and like review what some of the words mean, things like the null hypothesis, alternative hypothesis, look at what those significance levels look like, and then see if you can use your tables to find where those numbers are yourself. You'll feel a lot better about it. Next week, I'll start using the other formulas where we talk about more than one sample. So this was just for one sample for each of them. All right, thanks guys. And the sign-in sheet ended up here. If you need it. Yes.
I wanted to ask, I don't know how many questions it is, so I wanted to ask like, how many are left to
Email me, because I don't know off the top of my head, but I can look at a calendar and find you that number. And then I can look at how many you have. Yeah, just send me an email. Yes.
So like I know we were talking about this part in class, but what would this be?
So whenever it's just the alpha value, the alpha over 2 is when we're going to do a 2-tail test like we were doing for this one. And so you'll always take it and just cut it in half. Take it, cut it in half. Take it, cut it in half. So if it ends up being a 1-tail test like we talked about,
Then you would just use
then you would just use that one.
and then
Yep.
2. Okay.
Correct. I know, it's weird. It takes a little bit before you're like, what are all these symbols?
I mean, I find it
It's kind